which
Okay.
means you can share your screen so you can do your PowerPoints.
All right.
Do you know the icons at the bottom? There's one that's green that says share screen.
Let me see if I can get everything in my background set up so I can
Mm, okay.
launch something.
So what you need to have is the PowerPoint open, but not yet in slideshow mode. So you can have it open, and it can be at the bottom. Are you using a PC, Windows, or Apple? There you
Is that
go. That's it.
Yeah.
all right? Okay.
Excellent.
Now, how do I unshare to go back?
Um, at the top, it should have a view options, and it says you can. There you
Oh,
go.
thank you. It's new, but it
Excellent.
is like the rest of them. So that's, I was really quite worried about the sharing thing yesterday. So I was creating
Right.
fake meetings and trying it, and interesting.
Yeah.
Well, thank you for doing this. I know the time is not super great. I'm sure you're a little sleepy. Uh,
So, it's been a crazy week because I have been up at odd hours because I have to see what's going on in DC. Just had
Oh,
to
I
be.
I am actually in DC right
yeah.
now.
Wow, that's a great place to be. I
Kind
know you're
of. Kind of. The sad thing is, though, everything we couldn't get to anything. Everything
Yeah.
was locked down.
Yes. Yeah.
But last night I actually could see the fireworks from my window.
Okay.
So
Wow.
that was kind of exciting to see it on TV and then to
Yeah.
go see that.
Yeah.
And it was a really I thought it was a very, at least in my opinion, great inauguration.
Yeah. Oh, yeah.
So
Yeah.
given the circumstances,
Yeah.
better than what I thought they were going to pull off. I mean, I watch
yeah,
it from CNN and what we have here in cable news, but
right.
oh my gosh, it was a beautiful show. And,
Yeah.
I was worried that with the security, it was going to have an ugliness, just a physical
Mm.
ugliness.
Right.
Yeah.
But you didn't even notice that. The
The
flags were going.
flags I think that they put out were very pretty.
Yes.
Mhm.
And I love Lady Gaga. I think I can never
Yeah.
love her more, and yet I love her even more.
Yeah.
So
I
Yeah.
wasn't sure, Lady Gaga and,
oh,
oh,
she's great. She can do anything.
my brain is failing on Jennifer. How did
Jennifer
fail on
Lopez.
Jennifer? But they walked up, they nailed it. We got
Yeah.
back to being what I call a normal country, and
Yeah.
it was an absolutely phenomenal feeling to see. And
Yeah.
living as I do constantly overseas,
Mm.
the first thing that happened when Trump got the primary is my university. Like, oh, Roy, you've got to come talk about Trump. What does Trump mean to America? Like, do I have to? You know, and but now I have the lovely thing of talking about Biden and what it might mean for public international law and
Yeah.
things like that. It's
Yeah. Yeah.
Right. Well, Aubin and I and
Yeah.
Gina, who is our EENR Center co-director, were just talking about our two big conferences this year. One is the Energy Transition Law and Governments, the big annual meeting,
Yeah.
and then also our North American conference. And the transitions that are going to happen because
Yeah.
of Biden and energy and climate, of course, are there's a lot
Yeah.
to take apart, both in Canada, U.S., and Mexico, which is the North
Yeah.
American Conference, and internationally as well. So,
it's going to make a huge difference, really. I'm in Korea. I'm involved with the government's effort to go to a blue and then green economy. They're going to
Wow.
have Hyundai handle that. I don't know if
Wow.
you've seen that in the U.S. press yet, but they've already. There's a new scion who's taken over at Hyundai, and
okay,
so
Wow.
he's very avant-garde with his thinking.
Wow.
Some of his stuff will work, but the
Mm.
electrical cars, flying cars,
right,
the blue
Hmm.
right.
economy, and he's one of those folks who has billions of dollars to make stuff happen.
That's great.
And
Wow.
so they'll be
I
doing it.
love Hyundai, by the way. I own one of only two all ionic electrics in Texas,
Nice.
um, which is great. Very
Mm.
fun. So, okay, we're about 2 minutes out. So right about 4 Central Time, I'm going to
Mm.
open, and
Yeah.
it'll take a second to populate. People will be waiting and come in. Right,
Hmm.
you haven't done Zoom yet. I will
Mhm,
switch to what's known as a speaker view, which is what I'm
mhm.
doing now. So
Okay.
you are on the speaker view, but I can pin myself to it, or I can pin Aubin, or I can
Yeah.
pin you, which I will do when you're speaking. I'm going to start with pinning Aubin
Yeah.
because he's going to do the initial welcome, right? And then
Yeah.
he's going to pivot to me, and I will do your introduction.
Thank you.
And I'm so excited about this. This is so like new. I mean, I've heard of it, but it's really new for, I think, a lot of our audience. So it's pretty exciting. And so, yeah, you can just go as long as you need. People can ask questions through the chat function. And I will try to keep up with those, and Aubin can as well.
Yeah.
And then we'll just have a little bit of a discussion.
Looking forward to it.
Great.
Thank
And
you.
when Aubin and I aren't on, we'll mute ourselves so that there won't be feedback.
Yeah.
Okay. I'll just lay back and try to do the best show I can do.
I'm
Great.
sure you will. I'm sure
And take
you
your
will.
take your time.
Right.
You'll
Right.
see, it'll be quickly moving. I've got 81 slides for the 30 minutes.
That's, you know
Oh,
what, you
that's
can
great.
go, listen, you can go longer than 30 minutes.
Yeah.
Okay.
Yeah.
You
Well,
can.
some of them really are just images. See this, because it's such a new thing, and most folks have no idea. I was
Okay.
saying,
I think we are open. I think attendees are coming on
Okay.
right now. That's great. So welcome everyone.
Yeah.
And I will let Aubin take over.
Yes.
Probably give it another couple of minutes and then we can.
Hello, everyone. I'm delighted to welcome you all to in this session. Thank you for joining our virtual lecture with our guest speaker, Professor Roy Andrew Partain from the University of Aberdeen School of Law. I'm Aubin Nzaou, and I'm a researcher at the Environment, Energy, and Natural Resources Center at the University of Houston Law Center. And it's my pleasure to kick off our today's session. As part of our monthly guest speaker series on energy transition and climate governance, which convenes speakers to address topics relating to many challenges of our time as regards energy law and climate policy. Our program is funded by the European Commission in the frame of the H2020 program and Marie Curie actions. And our research covers a wide array of topics, including climate litigation, non-state actors, environmental governance, etc., under the leadership of Professor Victor Flatt and Professor Gina Warren. Our series will also feature the forthcoming guest speaker. February 16th, Professor Alexandra Klass from the University of Minnesota School of Law on eminent domain law as climate policy, March 12th, Professor Joshua Galperin from the University of Pittsburgh School of Law on uncommon law judging in the Anthropocene. April 29th, Professor Uma Autka from the University of Kansas School of Law on an energy law and climate related matter. May 19th, Professor Rebecca Brad-Spies from the City University of New York School of Law on an environmental law related matter. Then June 17th, Professor Lisa Benjamin from the Lewis and Clark School of Law on companies and climate change. For further information, please feel free to visit our website, www.law.uh.edu/EENR Center. From now on, I yield the floor to Professor Victor Flatt, our chair. Can you hear me,
Thank
Victor?
you. Thank you,
Okay,
Aubin.
okay.
I appreciate that very much. Once again, thank you for the great programming you have brought to the University of Houston Law Center as part of the Marie Sklodowska-Curie grant. It's a joy to broaden our connections internationally, since the issues of energy and controlling climate are first and foremost an international issue. One of the few silver linings of the pandemic has been a broadening of all of our reach to come together across distance, across time zones. We will have people from over countries from every continent outside of Antarctica, either on this or viewing it later. Today, I'm very excited to welcome Roy Andrew Partain from Aberdeen and Seoul as our Energy Transition Law and Governance speaker. Professor Partain is a chair professor at the University of Aberdeen's School of Law. His research focuses on mathematical models of legal rules and institutions, especially as applied to matters of sustainable development and enhancing the functioning of democratic institutions. At the University of Aberdeen, he lectures on mathematical models of law, comparative private and public law, and on international environmental law. He created the LLB with computing science, the first in the UK. He has also launched the LLM in business law and sustainable development, the first to focus on sustainable development for commercially focused lawyers, overlapping many of my own interests, including math. I'll have to talk to you more about that later. He is now relaunching Aberdeen's space law program, once led by Professor Frank Leal. His published research focuses on the theory of the anti-commons, on the theoretical models of climate change avoidance and mitigation, which is also known as the green paradox theory, on the foundations of environmental law and economics, on offshore carbon capture and storage, and on artificial intelligence's threat to law and social justice. He was originally trained in economics at Georgia Tech and the University of North Carolina, Chapel Hill here in the United States, and is a former banker at Deutsche Bank's headquarters in Frankfurt. During an FLAS fellowship in Korea, learning about law and the centrality of that issues of economic development, he also decided to go back to law school and received his JD degree from Vanderbilt University, and then graduated with his PhD in law from Erasmus University in Rotterdam. Prior to his academic appointment at Aberdeen, Professor Partain was a law professor in Seoul, South Korea, a professor of economics in Daegu, South Korea, and he has also served as corporate counsel for upstream affairs at both ExxonMobil and at Chevron Corporation. Related to that, and of note, he's had many forays into Houston, and we are glad to bring this connection back. EENR, the Environment, Energy, and Natural Resources Center, focuses on the intersection of environment, climate, resources, and energy, as Houston moves from being the energy capital of the world, which used to mean fossil fuels, to the capital of all energy and energy management, including renewable development and carbon management. Before I turn this over to Professor Partain, I want to just do a couple of housekeeping items. Please feel free to ask questions in the chat function below. in your Zoom, and we will try to answer those after Professor Partain's initial presentation. I also want to share our screen with you to show if you are receiving CLE from the state of Texas, that's continuing legal education, you may scan this course number. If you are getting CLE credit outside of Texas in the United States, you must report your attendance. And to get your certificate of attendance, you may email Tanisha Green at the University of Houston Law Center. Her email address is here, tcgreen3@central.uh.edu. If needed, I will show this again at the end of the presentation. So that's enough. I'm very excited to hear more about methane hydrates and the exciting future we're going to be having with them, I think. So Professor Partain.
Thank you. Thank you very much. Thank you very much. What I'd like first to do is to kind of break the ice here and to say that this is not a presentation that we are going to provide solutions. This is a presentation that does not tell you what to do. What this is a presentation to say that there is a phenomenally gigantic natural resource that is basically undiscussed in the legal literature. And I'm inviting everyone to take the time to learn about this resource and to consider how it will play into the transition policies as we move from a fossil fuel and other energies towards a sustainable, renewable energy future. There are both positive aspects that might be engaged from methane hydrates, and there are a lot of negative aspects from methane hydrates. There's a lot of area that should be thought of carefully, but if legal scholars don't start the process, it may, the research, the analysis may arrive too late. And we saw a lot of this situation with fracking. Fracking was a technology in the laboratories for several decades. Colorado had a major build out in fracking in the early 1980s. Then they shut it all down. They didn't have the economics. It remained in the lab, and scholars stopped talking about it. And then when it arrived again, it happened so quick, so fast that many fields were put into play before good regulation or good thought had occurred on how to environmentally stop and think, what does this do for agriculture? What does this do for communities? And what does it do on a variety of other fronts? Not to say to do it or don't do it, but we need to have a fully engaged democratic process to identify our environmental goals, our sustainability goals, our community goals, and to think about that. And it's best done before the actors are in play. So now is a great time to stop, learn, think, and make good critical comments on where there's good things to do, where there's significantly ugly things to avoid, and try to lay the best path possible. It may be we don't ever want to develop methane hydrates, and we need good legal scholarship to achieve that. It may be there's a safe way to use them. We want to get great scholarship for that. So please take this presentation with the most open mind possible. My goal here is to stimulate intellectual reaction. So you say, I'd like to write a paper on that. And that's my goal. That is my goal, is that you will go, that's interesting. My country, my community, my interest in the science or my interest in environmental law requires me to take that next step. And that's my request from the very beginning, my prayer to the court. And so if I can start to show a screen, and I don't know if I will remain on screen when it's up, but this is the slideshow. I hope everybody can see it. And I'd like to start off with this first slide, and then I will pick up a little bit of speed. I have around 81 slides, and some of them are a cascade of just images just to help see things because this is such a new thing. At the University of Aberdeen, we are looking at offshore methane hydrates. There are onshore hydrates in Tibet, in Siberia, in Alaska, and Canada, but they will not be the focus today. They're a much smaller asset. We're looking at it in our Center for Energy Law, which is known as OCEL. We're looking at offshore methane hydrates in the Center for Energy Transition. And we're also looking at it within our postgraduate research school, where we have a PhD student currently looking at offshore methane hydrates for Southeast Asia. And we've had a number of LLM dissertations written on it. when we talk about it as a topic of energy transition at Aberdeen, we primarily see it in these 5 vectors. One is our oil and gas and transition research. As we look at what happens to the future of petroleum and natural gas globally, it's important to remember that there is coal, crude oil, natural gas, and natural gas hydrates. Most people only talk about the first 3. Most people also assume that we're running out of crude oil, we're running out of natural gas, or at least we're running out of the easy stuff, so it'll all get more expensive. And I hope after today, you'll realize we cannot be so simplistic. Energy justice and access to energy is another aspect of energy transition. Many communities do not have what we would call an equitable access to energy or to fresh water. And water often intersects with the energy systems that the development of energy often implies the loss of water. And methane hydrates provides a very different way that that game plays out. And so we want to understand how it might impact or affect energy justice. The hydrogen economy is probably one of the big solutions that's being offered to the public right now, that there are ways to obtain hydrogen. Hydrogen's a lovely chemical from an energy perspective, and that the use of hydrogen results in heat and water, both of which are wonderful and useful. It doesn't create any basic pollution. There isn't any carbon dioxide. However, in the obtention of hydrogen, if you take it from natural gas, where you can take natural gas and steam and combine them in nice ways, you can get hydrogen, but you also get carbon dioxide. You can also use electricity on water to create hydrogen. So we talk about blue hydrogen, green hydrogen, if your electricity is from sustainable sources. Methane hydrates provides a very interesting ramp to blue hydrogen, and depending on how it's done, it could also be a ramp to green hydrogen. The hydrate, to take away the word methane from it, the hydrate reservoirs themselves are this icy sponge that can hold gas, particular types of gas, such as methane and carbon dioxide. And so as well as it holds methane in nature, it can also hold carbon dioxide. And so, for example, researchers in Germany at the Sugar project, and that's literally SUGAR, they've been practicing how to go to offshore methane hydrate reservoirs and inject carbon dioxide into the reservoir where the carbon becomes frozen forever. And finally, as you'll see, the geography, the geology, the environmental impacts of offshore methane hydrates will have a phenomenal impact on so many other aspects of environmental law, on climate change law, on energy law, that we need to really understand all of these interactions to ensure that we don't accidentally have a Frankenstein of climate science somewhere down the road. And so the unintended consequences thing requires a lot of forethought, and is both my lovely hosts in Houston and my students in Aberdeen are aware, I'm very interested in ensuring that climate policies coordinate, because the green paradox almost shut down in some ways some of the talks at the Paris agreements, and we want to avoid such problems if at all possible. But there are groups who would like to say, don't do it. So what we need are good answers on how to achieve green and renewable energy supplies, how to achieve a solid, sustainable energy transition. And I hope that I will be adding some very interesting story parts that you can include in your broader research. So what are the nutshell elements here? The good that will be there, why policymakers will want to have offshore methane hydrates in their commercial strategies, is the huge volumes. There's so much. There's just so much natural gas in these resources. It's almost stunning to think that no one has done anything with them to date. And that's another part of the story. There's literally centuries more natural gas than are currently discussed in most energy plants. It could also potentially double our access to fresh water. Not meaning we'll be able to access the old fresh water with more wells and more pipelines. No, the volumes of fresh water known to exist on the planet double. And that's an interesting and not frequent event that you discover more fresh water. The ubiquity, just how pervasively around the world methane hydrates are, is also another game changer from oil and gas. Oil and gas is you have the lucky geology or you don't. With methane hydrates, if you basically have a coast and a continental shelf, there's a very high probability that you have methane hydrates. For energy security, some countries like Korea, Japan, China, they are woefully short in all energy resources. And anything that provides their economy and thus their governments greater stability is something they're going to consider, even if perhaps it's not per se economic or genuinely commercially feasible, because it may offer them survival through certain choke points of other global events. Were the Persian Gulf to go into disarray, many countries on the Asian Pacific zone would have energy crises that would be very regrettable. And so for many countries, they may be looking at methane hydrates as a backup plan. That such giant reserves might come into the market could also change the prices that we see globally. And again, that would have very interesting implications for both energy security for countries trying to achieve some reserves or to achieve some safety and that they can buy what they need, but also for trying to get the economies of sustainable energy right and to get solar cells and windmills and other renewable energies into a sustainable path. If they have to face lower sustained prices from fossil fuels, we need to make sure we have more resilient strategies for those. Again, I've mentioned already the use of carbon sinks with methane hydrates, and the Germans have looked at it. The EU have very broadly considered this issue. I'll show you a map a little bit later of why Europe is getting so serious about offshore methane hydrates. We've been talking about it at the Commission for about a decade, and it's getting somewhere. Rampway to blue hydrogen economy. You've got hydrogen, you've got water. That's the key ingredients for traditional hydrogen processing. But you can also use the gas to create electricity to start up the industry of electrolysis for creating hydrogen offshore. And once you get the electrical electrolysis systems operating and you get an onshore economy working on hydrogen, then it's a much easier transition to swap out the source of the electricity for creating hydrogen. So a lot of countries think this might be a capital perspective on how to get green hydrogen operations up. And finally, there's so many revenue vectors that can be created from this. So there will be a lot of reasons policymakers are excited about offshore methane hydrates. There are many countries who are currently looking at it. At the end of the slideshow, I'll show you a list of the countries that I'm aware of that are currently considering bringing these online. Let's talk about the bad. It looks simpler list, but it's really not. It's just the nature of how paragraphs go. Methane hydrates are essentially methane. And methane in the ocean is a regrettable chemical presence. If methane gets into the ocean, you basically start to turn the methane will start to be metabolized. Methane is eaten by a lot of very lower levels of the food chain, and they will convert it into carbon dioxide. Carbon dioxide in the water turns the water into carbonic acid, and we wind up with water acidification in the coastal shelf. And that's not good. If you get methane at larger volumes, the methane will sustain in the water. That causes other problems, but you'll also wind up with carbon dioxide and methane displacing oxygen in the gills of fish and other sea life. So they'll choke for air. If those volumes reach the ocean surface, there's a variety of nuisance and dangers that are created when methane floats at the top of the ocean. The offshore industry has seen many ugly accidents where methane at the ocean surface resulted in fire and other problems. And if you wind up with methane in the atmosphere, methane is a far worse chemical than carbon dioxide for climate change. I think the routine number given is that methane is somewhere 20 times worse than carbon dioxide for climate change effects. All of that is not good. And I'm going to tell you right here, that's the good day. The bad day of methane hydrates is that if enough disturbance occurs at the bottom of the ocean, the hydrates will start to get loose. And if they get loose, the material above them, which is the seabed, gets loose. And if that gets loose, they slip and fall into deeper parts of the ocean. And when those kind of landslides occur, it's a gigantic mass, and the water that was down below before now cannot be there. And as that water moves up and out of the way of the falling landslide, you will get tsunami. And geologically, this occurs naturally. About 1 in 8 offshore sea slides, geologically and naturally occurring, no humans involved at all, are caused by methane hydrates. Hold on. I had one question thing pop up for a second. So if I could just come back to this landslide, and I'll get back to how we get the energy transition coming later. The potential for subsea landslides is that you have it's a bit early for me where I am, anthropogenic tsunamis near major cities. That's quite an ugly outcome. Instead of what we saw with the BP Deepwater Horizon, where you had a score of dozens or potentially hundreds of people killed, like we had at Piper Alpha in the North Sea, you're shifting to thousands and millions of people dead. If you flood Dhaka or Lagos with a 10-meter tsunami coming in, a lot of people disappear very quickly in very horrific ways. It is a environmental and social consequence that so far we've not seen in traditional oil and gas. You could also have very large chunks of hydrates coming up to the ocean surface. There are acute events of this. If you go near Vancouver Island in Canada, there are some hydrate fields, and they have very small chunks that come up to the ocean surface. So if you're fishing on the right day, you'll see these white miniature icebergs floating nearby, and they just sit there and slowly melt. Nothing dramatic happens because they're only the size of a basketball or something. But if it were to be large, acres of size or larger, it could be very dramatic. And of course, all that methane would be going into the atmosphere. And finally, and this is one of the first times we're talking about this publicly, is the military misadventure option. This was discovered by environmental scientists about a decade ago. It was raised at the European Union, and because there was no effective way to interact on that issue, we decided not to publish or discuss it publicly. And so we've been trying to figure out methods to prevent this issue, but there was some public scholarship on this that now requires all of us to become much more active on this front. If you can have the industrial accident by accident, well-meaning engineers having some mistakes in their planning, you can also do it on purpose. And when you have a gigantic asset of methane that is not miles deep under a rock, it's attackable. And just like in World War I, we know in the Italian Alps, the Swiss Alps, people would shoot at the mountains to get the avalanche to come down and to hit the soldiers below. Well, there would be ways to attack the methane hydrates that could cause tsunamis that could injure people on shore. And it has been advocated by some scholars, and thus we need to address that and suppress it as best we can. How critical is this? Well, the USGS says it's happening. Their chart of timelines of research and engagement around the world forecasts that somewhere in Asia, we will see commercial starts in the mid-2020s. Nobody knows exactly for sure. I can tell you that Korea is planning to be offshore with wells in the late 2020s. It may occur earlier. That's just the way it tends to happen over here. China has announced it will be doing it in the South China Seas in the 2020s, and Japan has long said it wants to be commercially viable before 2030. So there are 3 major states that are saying they're going to do it. Will it occur? It's always the harder challenge, but there is money, there is political action, and there is a public commitment to these resources that does not yet exist in other countries, but it will be an interesting thing to watch. We may not have a lot of time if it comes quicker. So let's get into a more interesting part of this. This will be my switch to the scientific world. What are methane hydrates? Well, methane hydrates look like snow, but they're not snow. This person is not holding something cold. It does look like ice. It will feel like ice, but it'll be around 10 degrees centigrade or around 50 degrees Fahrenheit. It looks like ice, but it's at room temperature. If you light it, you get hydrogen coming, the methane, which is carbon and hydrogen coming off of the top, When those carbon bonds break, you get the nice fire reaction. What you don't see is the carbon dioxide from the carbon coming off of the methane. And below, it'll drip off water. So this is not quite like crude oil, which is an incredibly complicated soup of chemicals, nor is it like your traditional natural gas, which doesn't really hold water in it. Because of the way that methane hydrates form in the ocean, there's nothing else in it. This is also slightly odd because normally when you produce natural gas, there's a variety of NGLs, natural gas liquids, and other kind of pollutants like hydrogen sulfide, H2S that would come up with the natural gas. Not in this case. The formation actually chemically processes everything out of the methane. Similar for the water. Although it takes ocean water, which is very salty, that water in the ice structure has no salt at all. It's a very unique process. In fact, hydrate formation is one of the technologies that's being considered for salination processes in Africa, where we could use this type of an approach to create fresh water out of ocean water. It's also a very dense form of energy. If you have a cubic meter of hydrate and you just let it go to room conditions, you're going to wind up with almost a full meter of water left. That's a cubic meter of water. And you're going to have about 170 cubic meters of gas. That's dense. It's not as dense as LNG. It's about half as dense as LNG, but it's a whole lot more dense than your traditional gas reservoir system in the Earth. So when I show you pictures in a few minutes about how much is out there, remember, this is not natural gas density. This is a compressed natural gas, as it were. And it's compressed not because of pressure, but because of temperature in the way it's held in the matrix. Where will we find them? You will find them somewhat onshore. You will see that in the permafrost, there's quite a bit. You'll see these nice photos out of Russia where in Siberia, there's these nice new craters showing up. And that's where methane hydrates have warmed up. The methanes have created pockets, and at some point they explode. But 99% of methane hydrates are offshore. And this is a page taken from the researchers who were doing the Sugar project in Germany. And as you can see here, they label it as the methane hydrate in Kontinentalrand, which is in the offshore shelves, and in the Tiefen Kontinentalrand, which is in the deep offshore. It is primarily in the deep offshore, and the further offshore you go from a water depth perspective. So if you have very shallow water for a long way, that's not what I'm talking about. But as the water gets deeper, that puts pressure on the understructure that enables even deeper and deeper accumulations of hydrates. So this is what it would look like if you went and saw a scientific scan. And the first area where you just see the horizontal lines, that's ocean water. And then there's a tiny little bit of seafloor, that's mud, basically mud. And then you have the hydrate stability zones, the HSZ. That's where the hydrate is. And at the bottom is ocean rock. So you have water, a little bit of mud, a lot of hydrate, and then the ocean's crust. This is why we didn't know about them. It wasn't really until the 1970s when Soviet and American military technology working with sonars and submarines had trouble getting their measurements right at the ocean floor. Where is the ocean floor? Because it would hit the bottom of the ocean, and sometimes the response wasn't what they expected. Eventually, it was discovered that there was this gigantic amount of ice underneath the ocean mud that no one was expecting to be there. There's 3 ways to produce methane hydrates. The first one is inject hot water. So if you can imagine, your mom brings home a lovely ice cream cake that's covered in fudge, and you want to get some of that ice cream, but you don't want your mom to notice. You get a straw, you blow down some hot water, and you suck out some of that ice cream goodness. I wouldn't recommend that with a methane hydrate, but that's the basic concept, that you can use hot water to melt out the ice. As the ice is melting, the methane will release, and then you can extract water and methane. The next way to do it is you suck out vacuum, and that basically just pulls the methane out of the ice structure. And the third way is to flush it out with carbon dioxide. Now, in this manner, you put down carbon dioxide, it goes into the hydrate, it pushes out the methane, so you extract methane and inject carbon dioxide. The Japanese research has focused on trying to achieve that as a cycle, that they would lift the natural gas, combust it offshore, turn it into electricity, capture the carbon, send it back downhole, and then run electricity onshore. That way they don't have to deal with the dangers of pipelines, because Japan has a lot of earthquakes, and earthquakes and gas pipelines are not a happy combination, and electrical lines are cheaper. So if they were able to lift the methane, capture the carbon, send it back downhole, preserve the stability of the hydrate reservoir, run electricity onto shore, that's the way the Japanese are looking at this. So again, there are quite some differences in the way offshore operations may occur. And here is a visualization that the Chinese have put out. And when I refer to Chinese, I refer to the People's Republic of China, and they have a very large engagement in this area. I was first in Beijing presenting this to the Ministry of Finance and other universities in 2017. The same time they went public in China announcing what they'd achieved. I was there that the week they made the announcement. They have designed a concept where they would have boats come in and drill and produce locally, and then after about 10 years, relocate the boat. The interesting thing about gas hydrates, which is quite a bit different from traditional natural gas or crude oil, it is not a mineral that runs away from you very well. Traditional oil and gas remains very mobile underneath, but in a frozen structure, it does not. So as you produce methane hydrates, it produces radially in a circle distance from the wellbore. And so eventually you have to relocate in order to get the next bit over. Again, very important to say this, it is technologically feasible now. This is not over the horizon technology like nuclear fusion. It is technically feasible now. Japan achieved this in March 2013, and China achieved it in 2017. So Japan has had it for close to a decade, and China has had it for about 4 years. Now, mind you, these are the public announcements. There's quite a bit that is not publicly announced, and some things remain a mystery. But we do know that this technology is feasible and operation. And at this point, we've seen quite a bit of success from China and Japan as they've tried in different strata of the methane hydrate reservoirs. And things that back in the noughts, in the 2000s, before 2010, if you'd have gone to methane hydrate researchers and talked about what was feasible, what was not, you would have been told that only certain hydrates would have been producible, other stuff wouldn't be. The Chinese now can do those things that couldn't be done. And so the amount of resource in play is dramatically larger than people originally thought. And again, partially that's because not everybody will go about resource exploitation the way that Americans or Europeans might consider it. There are other ways to get things done. And if you change your mental envelope about how to solve problems, you wind up with different results. So let's look at a photo gallery. This is like our uncles and cousins. That's hydrate, close up. It's not the rocky stuff, that's sand, that's ocean sand, but between it, that's the hydrates. And so hydrates are kind of like a concrete structure where the hydrate cements sand together. But again, a little bit of heat, a little bit of vacuum, and the whole thing comes apart. That's hydrate structures removed and on boat, except for picture F. So A, B, C are core samples that have been removed from the bottom of the ocean. And as you can see, it looks like muddy snow in various states of pretty or ugliness, depending on how integrated the mud and the hydrate are. There's a chunk of hydrate sitting on the bottom of the ocean without much covering on it at all. There's another chunk on deck of boat. Again, mud and snow. That's the visual. Hydrates, unlike crude oil, are a fairly normal part of the marine environment. In fact, the European Union protects environmentally certain methane hydrate fields because of the way that they engage with bivalves. And so you will find crustacean and bivalves are often frequently around hydrate structures that are close to the surface of the ocean, because a small continual amount of methane is okay. That feeds into a variety of lower food chain bacteria and those kind of plankton things that then feed into crustaceans and bivalves. Again, at a certain natural rate, not engineered large-scale accidents. So it's not quite to say that everybody is happier with more methane in the ocean, but in its natural place, in its natural way, is quite fine. Here is a chunk of hydrate covered in mussels, right? So it's not lethal in the way that pouring crude oil on these creatures would be. So let's talk about the energy aspect if we can. 15%, 15% of offshore methane hydrates mass is simple sweet natural gas. It's a huge amount there. Huge amounts of timeline have been added to the energy horizon. So let's look at this. That green slice is the 1% represented by conventional natural gas. And the red in that circle is the amount of natural gas provided by methane hydrates. In the green letters, if you were to look at BP's annual statistics on how much natural gas is known to exist on the earth, they will tell you that there's about 198 trillion cubic meters of natural gas in conventional and tight gas and coal bed methane as they currently know where it is. Ingalls, Oss, and Lee have taken a slightly different approach to measuring natural gas volumes, and it's a little larger. And that's probably because they include things that will never come into production, just as a simple scientific how much actually is out there question. If we look at the estimates of volumes for methane hydrates, and that's what you see there in the red, and if you compare that against the BP number for conventional gas in play, we have some very interesting multipliers. You'll notice on the left column, the 30 U.S.C. 2001 reference. That is the U.S. statute that provides research funds in the United States for methane hydrates. And in that statute, they provide an estimate of how much methane hydrate they believe to exist globally. So there's actually a global estimate in the United States code. I don't know if you want to take that as genuine, hard, raw science, but it is an interesting indication of well-thought people who have gone through Congress. And that number suggests there's over 100 times more in methane hydrates than there is in the known gas industry. So we're talking about a huge, large amount. Now, at the bottom of every slide, you may have noticed there are citations. And if you need a copy, I provided a copy of the slides to the University of Houston Law Center. I'd also be very happy to send you a copy of the slides for your own use later, and very glad to help you identify any of the literature that supports the data here. I am not a physical scientist, so I do rely on published academic literature, but the numbers and things that you'll see here sometimes do shock what people were expecting. And so I do ensure that the footnotes are here for everything. Again, at the US DOE's National Energy and Technology Laboratories, they have also scoped out the potential play for methane hydrates. That pyramid in the middle with the red tip top, conventionals. They label it simple, conventionals, thousands of TCF. If you drop down to the next orange where they have tight gas and shallow shales, thousands of TCF. If you go on down to the coal bed methanes and deeper shells, they say the tens of thousands of TCF. And methane hydrates is the 100,000s of TCF in the plural. Then they pop out another pyramid to the left and they say, well, above the dashed red line is the stuff that we'll probably produce, and it's only in the tens of thousands. There is scientifically the hundreds of thousands of methane hydrates, but we're not likely to produce that. And then the Chinese come and go, excuse me, I did it. This chart on the left from Lee demonstrates where the various testings have occurred at what types of methane structures, and that in 2017, the Chinese did produce from that most difficult type of hydrate structure. So it's all in play, potentially. I wasn't on the Chinese deck when it occurred. I couldn't tell you the total veracity of it, but I will tell you that from journals that are held in very high regard have published this after peer review, and it is seen as very reliable what they claim to have done. If you consider the amount of natural gas that the world currently consumes annually, then what we have is a shift from about 50 years of natural gas capacity to 1,000 to several thousand years of natural gas capacity. And it's a heck of a thing if you're thinking about green energy policies and energy transition. If you've built your energy policies assuming that fossil fuels will run short or run expensive, to find out that there's this huge heaping pile of it that wasn't involved in those calculations. So we need to keep this in mind. Where is it? Well, back in 2005, Claude and Sandler, again out of Germany, made this forecast looking at ocean conditions where we ought to be able to find methane hydrates. And that's a pretty interesting chart in that pretty much every coastline has methane hydrates. There are some that don't. The east side of Malaysia, the tip of Brazil, but If you're in the United States or anywhere North or South America, there's hydrates offshore. If you're anywhere in Africa, you have it offshore. The Mediterranean on this map does not reflect data that we now have. That Mediterranean soaked in methane hydrates. And so it's a game changer for who might have energy resource. If you're a coastal state, you probably have it. Now, since then, people have gone and drilled and tested. And this is a map from the UNEP, which is the UN Environmental Program. And this is their recording of where people have hydrate success. Let's go a little closer up. Here's the Gulf of Mexico. And again, this is from Meritus. This is the MMS. This is fairly stable science. They're forecasting around 600 TCM, which is about 21,000 TCF. The Barnett Shale, a very large field in Texas, only has 53. As far as I can get numbers, this is a big step up in volumes. In the EU, we have just completed a very large study across all of European waters, and the orange on that map does not reflect a love for the Netherlands. The orange there is where pure methane hydrate stability zone around Europe. That's a quote from the Minshall report that came out in January 2020. In blue represents where there will be hydrates, but not as pure. That's a lot of hydrates near Europe and in the Mediterranean. And so now these red squares are where the highest density. So if you're in the Eastern Mediterranean, if you're in the Black Sea, if you're off of Ireland, how often have you heard Ireland talked as an energy production center? And of course, Greenland and some of the islands north of Norway. Japan, back in 2005, 2006, they came up with this estimate that they had 50 TCF, but that was before they went drilling, and that was before they became producers. They have not had a public announcement since on how much national reserves they may have. So the number is old and likely way smaller than what they've got. It's interesting that Japan, which has no energy resources before hydrates, has a giant amount of natural gas near all of its industrial centers. It could be a major game changer for their economy, for their economic recovery, and for them to be able to have some stability vis-a-vis geopolitics and other places. The South China Seas, which is between Vietnam, China, the Philippines, and Malaysia. What the current research there, and you'll notice I have several reports at the bottom for this one, they believe that they are holding somewhere around 270 TCF of gas. And for their purposes, they say that's about 200 years of energy security. You can see why China wants to go into the South China Seas and hold it. If you see that pink and you follow the red arrow, those methane hydrate deposits are 700 meters thick, vertical natural gas in a compressed form. And that is basically all the way from Vietnam to Manila. 700 meters, 2,000 feet of play. That's a lot of resource, and that resource is 170 times denser than traditional natural gas. So it is a very major resource. And again, when they say they have 270 TCF, I think you probably want to add a 0 or 2 to that, just given the way that these numbers get publicized. Indonesia, which has been a bit more transparent, has over 1,000 TCF in known fields. India, also major asset holder. And we know off of its far east coast that you do have fields that also have that 700, 600 meters of hydrate play. And those are where they hold some islands. So there is not a large land mass in the area, but it is a lot of resource. India is very heavily investing in it. New Zealand has methane hydrates, both coast, both islands. If you zoom in to see what you see in South America and Mesoamerica, the West Coast is amazing rich. We know Brazil, Venezuela, Colombia had crude oil, but now Argentina, Chile, Peru, everyone in Central America will have quite extensive resources. Honduras may actually be the country that falls short just because of the way its EEZ plays out. So again, looking at it globally, they're everywhere. Now, we were just talking about it as it was purely a natural gas play, and it isn't. In fact, it's not really a natural gas play. It's a water play. And this is where a lot of our research at Aberdeen is currently focused. We have a PhD student focused on the water aspect currently. If we look at the water available to us on this planet, there are 3 spheres there. The large sphere to the top left is all of the water on the Earth. The medium-sized one to the top right is all of the liquid fresh water. But the teeny tiny one, and let me zoom in, that teeny tiny one over Atlanta, that's the accessible fresh water we have. We have access to a very teeny tiny amount of fresh water. We can't go take away the permafrost and the glaciers and Antarctica, and we certainly don't want to be melting all that stuff for our use. So we have accessible water problems. We're going to need more water. This was recently. That's droughts. This is from the UN, and I actually have taken this from a US website, but this is UN data. And that's the forecast for the next decade out. If I can toggle that back and forth to highlight the changes, a lot of areas are going to need a lot more water really soon to avoid humanitarian disasters. We're going to need more water, and we don't have access to a lot. But luckily, you might want to think about the hydrates, because we can use the molecular calculations. We know how much carbon and how much methane. We can do a mass balance to see how much water is present. And so here I've run that calculation for you with the implied fresh water, and then compare that to our known accessible freshwater reserves. If you look at the US 2001 citation, we're basically talking about a doubling of access to fresh water if you produce the methane hydrates. Not saying you should, simply you could. These are gigantic freshwater aquifers that are barely discussed in the legal literature. They are barely discussed by most people talking about waters or droughts or shortages. And one of our questions is why? Why is this so discussed? We have a similar project running with the UN Convention on Droughts and Desertification. Why did the UNFCCC become so popular in the literature, but not its twin, the UNCCD? Both come from 1992 Rio, and yet water and economic accessibility to water is far less interesting to legal scholars than the issues of climate change. But a lack of water will kill people quicker. If we look at hydrates next to where the droughts are expected to be, the adjacency is quite interesting. The mountain range north of Thailand and into China, the Himalayas and Yunnan province, and where a lot of China's rice growing zones are, droughts are coming. If we look at the American West, it looks not happy. If you look at Chile, if you look at Southern Africa, you have a lot of droughts forecasted, but there's hydrates and freshwater aquifers right offshore that you would not have to disrupt your rivers, your lakes to get access for. And the ability to not disrupt the freshwaters that are in play in the local ecology. Now, again, if you add water to the cycle, it will become a globally available water because you use the water, it evaporates, it goes into the ocean, it goes into the atmosphere. Once you extract it, it does go into play in many interesting environmental vectors, and it's a bit unforeseeable what those outcomes would be. But you can see why somebody looking at a drought in their country, knowing that there's an aquifer offshore, might say, you know what, tap that, we want that water. You know, we need that water now, and if there's problems in 2 decades, the next generation can handle it. The same way that climate change was kicked down the pipe, that, you know, people did know about it earlier, but they thought we have other fish to fry right now. We'll come back to climate change when we got these other things achieved. Something to think about earlier.
Professor Partain,
yes.
I'm just going to interrupt you for a second. This is so amazing, but in the interest of time, I think what we're going to need to do is do a stopping point here, and let maybe have a couple of questions or summary, and then invite you back for another hour of this if you would be willing to do so. We could connect the recordings. It's astounding what you bring up.
One more minute.
Yes.
And
Yes, of course.
Go very fast, and then do exactly as you say otherwise, just so that folks do get the benefit of seeing the slides. They can download them later.
Perfect.
If I could just say very quickly, the UNCCD already signed by everybody. We didn't get the trouble with America on, like we did with the UNFCCC. Everybody is signed. Everybody's fully on board. There's obligations here that if you have technology, and understandings about how to get fresh water, it's incumbent to share the knowledge, to finance it, to enable that. That, though, could open up a Pandora box of what then happens with many countries who have never done deep offshore, never had the engineering, never had the coast guards, the boats, or any other way to verify what's occurring offshore, now having to figure it out before they tsunami their people. The environmental risk, just to give a very quick look at this, we've known about them for 20 years. The Japanese published it. We've republished it in English almost a decade ago. We know how the chemicals come through the ocean, and we know about the tsunami risk. If you get unstable hydrates, they start to slide. We can see how the tsunamis would come out of this. 1 in 8 already, without human intervention, of subsea landslides over a geological scale are hydrates. We know where those have historically occurred. A lot of those are near areas. Houston and New Orleans sit in a zone of danger. East Coast of the United States, we have methane bubbling now. If you go off the coastline, if your boat is in the right spot where these dots are, you'll see methane hydrate bubbles. We also know that's where gigantic landslides have occurred historically. Notice those landslides are the size of Massachusetts. If you can imagine Massachusetts sliding into the ocean, it gives an idea of how large the water displacement is, and that's power of the tsunami. We can lay those maps together to reveal it. In Scotland, 8,000 years ago, we had a similar event called the Storegga slide. The Shetlands were hit by tsunamis that were 60 feet tall. Scotland, especially Aberdeen and Montrose, were hit by waves 3 to 6 meters tall. That's really high water. Down in Montrose and also in Aberdeen, if you dig underneath the peat, you'll discover that a foot of sand was deposited in minutes. So it's peat very deep, and then a foot of sand, and then peat again. Normally, we don't get sand in Scotland. That's not our coastline. That stuff from far away brought in very quickly, and whoever was living on the coast that day disappeared. So we're going to need some monitoring technologies. Japan had some installations in 2013. This is the Chinese proposal that involves all kinds of the most cutting edge science and technologies, but it would require a lot of preparation to get done right. Military adventurism. Raja Raman and Rao have advocated the use of methane hydrates as weapons. They provided us this nice handy cartoon of how you can attack the hydrates. If I can come back here and give you a tiny quote. In gas hydrate explosion uses a surgical strike, the collateral damage is totally avoided. It's a strange phrase. By creating a firewall, by simultaneously bombing from aircraft and through submarine operations from ocean bottom in a restricted selected area. Of course. Why would you do it everywhere? And they basically say exploiting methane and methane hydrates in continental slopes is a better surgical strike than conventional ones. The advantages are more in this type of attacks than conventional war with nuclear weapons, because with nuclear weapons, you have radioactive fallout. And as we've seen from various movies and real life situations, Chernobyl and Fukushima, you may not want to move back to where they were used, but a tsunami 2 days later is probably very viable again. When you look at the risk to communities posed by people figuring out all they need is a World War II landmine to drop on oceans to create tsunamis, it could be something. So the world probably needs to be thinking, how do we secure our oceans from environmental interaction of a negative type? So these are the countries that are looking at doing it soon. These are countries that have had it in discussion. I'm begging for more voices to the research. I give you questions that are known to be open that nobody has yet written on. There's a lot out there. So for students who are wondering, what can I write on? What can I talk about? Here's a handy list of stuff that somebody needs to get to. Here is the extant legal literature. The names in blue are researchers at Aberdeen. If you'd like to see some videos, here are some excellent sources. I highly recommend watching the JOGMEC video, which is how the Japanese did it in 2013. This is not your grandfather's offshore oil well, and the Japanese will make it very clear. Thank you. All right, and I will stop sharing and we can go back to Q&A.
This is so fantastic, and we will post the PowerPoint with the recording, and we don't really have much time. I mean, what you're talking about is so enormous in terms of water, in terms of energy, in terms of security, in terms of warfare. it kind of is a lot really to take in, I think, for people who haven't really been exposed to this. And as you say, there are so many legal questions to look at. And I think I'll be using this list in my international environmental law class for one thing. But we really just have time then for really just this one question. And I'm going to see if you can at least provide a partial answer to this. So clearly, you are telling us that you feel like we need a legal infrastructure that is ready to handle what is coming. And we have a question about specific regulations as opposed to, say, oil and gas. And I'm guessing we want some very specific things to methane hydrates, not just oil and gas. So I guess the big question, maybe you can finish with this, is do you see more the answer more in sort of some kind of international law and sort of treaty law or something, just using the no transboundary harm thing? Or are you really thinking what's going on here, where the research is going? We need to be thinking about domestic law. We need to be thinking about the domestic law in Japan, in the United States, and in Europe, the EU, to get all of this going. And I'll let you answer that. Give you the last word.
Thank you very much. And it is exactly I think the right way to start the sequence of questions, in that I think the EU has an approach where we start with European directives, but also engage in state implementation. And I think it's the yin yang of it, in that we are going to have incredibly detailed domestic enactments. For example, just EIA processes alone. Most countries won't have had the scientists or the experiences to know what to put into the EIA process for frozen energy ice under mud. When they think about energy, they're thinking about miles of rock, salt domes and rock structures, and they don't have that exposure. Even the United States, for all of its exposure to oil and gas law, since 1840 with Drake, we don't have a lot of people who know this stuff. You could probably take one classroom and put all the methane hydrate people in that room. And if you start cutting them up between oil companies and other people who are interested, we don't have global expertise at the level that's probably called for. So we need to be able to focus on country by country details. Two of us from Aberdeen spent a year in Japan, helping Japan start to sort out their EIA thoughts. I'll be in Indonesia next month, helping them to try to start thinking about these issues. One of our PhD students, Kafa, is from Indonesia, and he's been working on this for 2 years. And we're going to be sharing some of his early results on where Indonesia's ready or not ready. But it's got to be detailed domestic. But just like climate change, because this is climate change, and just like the UNCCD, because this is water and droughts and people dying, it requires an international treaty.
As I said, we want to have you back to continue this discussion after we've posted this, and maybe it'll even generate some more complex questions that you'll be ready for. I want to thank you so much. I really have enjoyed this, and I'm so interested. And I enjoyed your paper as well. So very, very good. I guess that our time is up, and we've told ourselves we're going to keep to the time. I want to thank you. I want to thank our audience. This will be posted, a recording along with the PowerPoints should be posted on EENR's website under the Energy Transition Law and Governance webinar series by tomorrow. And we urge you to go there, and we will be following up with this. So thank you so much.
Thank you very much for the invitation. It was a pleasure to be here today. Thank you.
Signing off. Thank you. Bye-bye.
Bye-bye.